Hello, so for my gold project, I decided to do elastic collisions. And so elastic collisions are essentially where you have two bodies colliding and they preserve their momentum when they collide. So um, given their masses and relative velocities, um, their combined momentum will remain the same both before and after the collision. And so you can see in this Wikipedia GIF right here, kind of what that really means. Where if you have two billiard balls or something bouncing together, then they will bounce off in opposite directions with relatively the same speed. And so I've implemented that in Project Zero. And so if you see here, you can see that if I run the original one, then see, this is the Chaos Blossom scenario, and you can see right here that it's forming this kind of blossom shape right here. There don't appear to be any really collisions here that are occurring. Everything that is flying off the screen is occurring due to gravity. And if I start up the extreme version where you have elastic collisions implemented, then you can see a pretty huge difference here. So you can see very clearly that stuff is colliding. You look at some of the closer, like that collision right there, you can see that very clearly things are colliding off of each other. And so essentially how this is implemented is the overarching view is that if two bodies are sufficiently close together, then we say a collision has occurred. And so if a collision has occurred, then we need to update their relative velocities based on their post collision velocities according to conservation of momentum and elastic collision calculations. So that formula is taken from the Wikipedia page over here. So essentially, we take this formula right here, and then we plug it into the update loop. So we originally had an update loop that only updates relative velocities and positions based on forces, but essentially what this does is after updating all relevant positions and velocities due to gravity forces, we then check for collisions post update. And if there's a collision, so say if two bodies, the distance between two bodies is less than 10 to the ninth, then we say collision has occurred, and then we use that formula based on the relative velocities of both bodies, and then we simply update their velocities based on their masses and their velocities calculated using this formula right here. And so what this allows us to do is it allows us to reliably calculate elastic collisions and their effect on the bodies, and two, it allows us to do this in a somewhat efficient manner. Obviously not the most efficient possible, as it's n squared, but it allows us to do this for a fairly large number of bodies, as you've seen in this demo that I'm playing right now. And essentially, this allows a far more realistic simulation compared to something like the simulation we originally had where elastic collisions were not implemented. And now obviously this isn't entirely realistic compared to real life, because real life planetary collisions or something like that would likely be a combination of inelastic and elastic collisions, and there would also be slightly significant fracturing within each body. But obviously that's a lot more complicated to model and won't be covered in my modifications. Further way to further optimize the kind of performance of this elastic collision simulation is to perhaps instead of calculating using delta time steps and then doing an O of n squared check every time to see if stuff is colliding, we can use some sort of data structure similar to a priority queue, where we keep track of what is about to collide in the next time step, and every time we step through the simulation, we essentially calculate the collision, and then we update all the relevant forces, velocities, positions, etc. And then we update the priority queue with any new possible collisions that are likely to occur based on the vectors of two bodies. And essentially that allows us to uh, do this in O of n log n because insertion into a binary heap is O of log n. And so this allows us to do a much more efficient calculation of elastic collisions than the naive O of n squared solution presented here.